At this point, we've covered the basics of probability theory, so we'll be able to turn our focus on the algorithms themselves and their analysis. Up first is the classic randomized quicksort algorithm.
In case you don't recall randomized quicksort from a previous algorithms course, here's the pseudocode. To keep things simple, we'll assume that the elements to be sorted are distinct. This is a recursive algorithm, with the base case being a list of 0 or 1 elements, where the list can simply be returned. For longer lists, we choose a pivot uniformly at random from the elements of the list, and then split the list into two pieces. One with those elements less than the pivot, and one with those elements larger than the pivot. Then we recursively sort these shorter lists, and then join them back together in sorted order like so. The efficiency of the algorithm depends greatly on the choices of these pivots. I'm going to visualize a run of the algorithm by drawing out the recursion tree over here. I'll write out the list in sorted order so that we can see better what's going on, though the algorithm itself will likely have these elements in some unsorted order. The ideal choice of pivot is always the middle value in the list. This splits the list into two equal-sized sublists, one consisting of the larger elements, the other consisting of the smaller elements. Then, in recursive calls, we split these lists into two pieces until we get down to the base case of a list of length 1 or 0. Because the size of the lists get cut in half with each call, there are only log-n levels to the tree, and every level gets compared with a pivot in a call to quicksort, so there are order n comparisons at each level, for a total of n log n comparisons overall. That's if we're lucky and pick the middle element every time. How about if we're unlucky? Suppose we pick the largest element in every iteration. Then the size of the list only decreases 1 in each iteration, so there are n levels. The first level requires n-1 comparisons, the second n-2, and so forth, so that the total number of comparisons is an arithmetic series, and therefore is order n squared. This is as bad as a naive algorithm like insertion sort. The natural question to ask then is, how does quicksort behave on average? Is it like the best case, where we pick the pivot in the middle of each list? Or is it like the worst case that we have here, where we're always picking the largest element in the list? Or is it somewhere in between?